Okay, we're going to try something different. We're going to try only the desktop and not myself, since seeing me is not super important to teach you guys about fuzzing. Okay, let's just do the desktop. Let me know what happens. How's everybody doing now, sound wise? Okay, perfect. Someone said much better video quality. That's fantastic news. Okay, all right, good. We don't need to see me. We just need to see all this. That's the important part. So let's get started again. I might have to skip one or two things to get through, but we should be able to still give you guys a good overview of fuzzing. Thanks for sticking around through all of that. Hopefully it wasn't too bad. But anyways, so back to mutational fuzzing. Okay, so as I sort of said a couple times, I'll do a very quick recap this time since apparently I was quite choppy. But so we started off by showing you how Radamsa works, and Radamsa is a tool that sort of takes a bunch of inputs and then sort of mutates them, changes things, adds things, deletes things, and with the goal of trying to turn the input into something that the program you're testing hasn't seen before. So for example, if we were to run it on this example.json here, we can see that, look, so it decided, hey, what we're going to do here is we're going to duplicate this this parallel line, right? So there was just one here, and now there's two here. And it's actually duplicated the whole section. As you can see, we also have this abbreviation part twice. So what Radamsa is really good at doing is sort of working out at a very high level what might be structurally interesting to change about an input, so that it produces a bug. And that can be really useful because you've your developers have thought of some tests doesn't mean they've thought of all tests. And a great example is this buggy program that we're going to be fuzzing first. So it's a program that just looks at these three words and tries to count how many of them are in the string. So if the string contains foo, it'll print 1. If it contains bar, it'll print 2, and so on. And we can actually try that out and see how it works by just running the actual program and then telling it to look at a file. So if we actually look at seeds1, we can see that it just contains one of those strings, and of course we got the number 1. So that works, and we can run through the other ones too, and ensure that our program works. And so this is sort of the introduction of a new concept, the idea of seeds. And you can sort of think of seeds as your unit tests. They're things that you're giving the fuzzer to start off with. You're saying, hey, these are some things that I've tried that have worked and that produced the actions that I expect from my code. And so what a fuzzer is really good at doing is taking seeds and things that you've said work properly in your code and actually turning them into something that'll break your code. And so to actually break this program, what we're going to do is we're going to use the smallest fuzzing program in the world called fuzz.sh. And it's just something that we're going to walk through now. And so the desired usage is we want to run this program with the thing we're testing, and then just a directory of all the seeds, which is the directory of all the unit tests that work right now. And we're going to start off by essentially just with a while loop. And the reasoning for that is, as a fuzzer, you're not sort of bound by, you're not a developer. You don't have to, stop after a certain amount of time. You can run forever. And so we want to run until we find a bug, because if we don't find a bug, there's always more inputs to try. And if we have found a bug, then it's time for the developer to take a look and actually fix it. And so the first step is to generate a test case with Radamsa. And so as we saw before, we can just give Radamsa a bunch of files and say, please generate a new test case and put that in input.txt. We're also going to display the test so that we have a bunch of information running across the screen while we're waiting for the fuzzer to find our bug. And then we want it to execute the program we're testing. So the program is the first argument there. So we're just going to call program1 with input.txt, and we're going to send all the results to dev.null because we don't really care about what the program outputs right now. We can look at that again later. And then this is the interesting part. If the program crashed, we want to save the input and exit. And so this is a Go program. This will work on, by the way, in terms of like what code this fuzz.sh will work on. It'll work on anything that takes that reads input from a file. And you could very easily modify that to fuzz anything that takes input over a network via curl, or it takes anything via standard in by using a pipe instead of a file. It's pretty versatile. It's just a bash script. So anything you can do with bash scripts, you can do with this. And so if the exit code is greater than 1, then we've found a crash, and we're gonna make sure that we save the input, say, hey, we found a crash, and then we're just gonna exit. So let's run our little fuzzing program. Let's see if we can actually find the bug. So we're gonna run fuzz.sh. We're gonna give it the program that we're trying to fuzz, and we're gonna say, hey, all of my tests are in seeds. We're gonna run it, and as you can see, it's starting to fuzz, and you can see all of the inputs running across the screen. So the fuzzer is trying to, and there you go. It actually interrupted me and found the crash early. So there you go. That's our first fuzzing bug. And now let's take a look and see what it actually is. So if you look, you'll see that there's actually all 3 strings in here. There's the first one, the second one, and the third one. And if we go back and look at our program, it turns out that we actually made a little error there, where if we increment this counter all 3 times, we get to I = 3, and as we know about arrays, that's an array index out of bounds. And if we were to actually reproduce this crash using the program live, we can say, hey, run this, and it'll panic and say runtime error, index out of range. So that's sort of a first example, little example of how fuzzing works and how it can be used to catch bugs that developers miss. So moving on to the next topic, I'm actually just going to check and see if there's any different from. So is this different from the find bugs like plugin by the fact that it generates extra tests, more complex input data, and so on? Yeah, essentially. So the power of fuzzing is really that it can sort of infinitely keep generating tests. So the nice thing about that is that if there's one very specific input that's going to crash your code, you can sort of use fuzzing to eventually find that, because if you have so static analysis is basically a tool that sort of reads over your code and sort of like a spell checker and looks for things that could be wrong. But so this is different from find bugs in the way that it actually executes real tests. So if a bug is found, it's not, hey, maybe this is an area you should look at. We think it looks strange. It's this is an input, like a real input that we have for your program that we know crashes it. So fuzzing allows you to be a little more certain about the results that you're getting. That was a good question. So very quickly, I'm going to go over grammar fuzzing. And I say very quickly because this is sort of an addendum to mutational fuzzing. So grammar fuzzing, again, you can check this all out yourself. But grammar fuzzing sort of, for this, we're going to use something called Dharma. And Dharma is very similar to Redamsa in that it's a simple command line utility that you can throw into whatever script you want. But instead, it generates tests from a grammar. And this can be useful for many reasons. So for example, if you're fuzzing something that parses JSON, and you want to make sure that even if it gets a very strange looking piece of JSON, it can still, it can still say, hey, this is valid and that it conforms properly to the specification. You can use Dharma to do that. So I have Dharma installed on my machine. And I'm just going to say, please, generate some tests using the JSON grammar. And so you'll see here, I have 2 grammars. I have a JSON grammar and a URL grammar. And a grammar is essentially just a definition of a language. It sort of specifies all the possible things that can happen within a certain definition language. So here we have, JSON has integers. We know that it has numbers. It has certain escape characters. It has actual straight up characters. It can say what a string is. So it sort of allows you to define the entire specification of what an input language looks like. And if we run Dharma with the JSON grammar, as you can see, it generated some strange looking JSON, and that's good because what we want is Dharma to generate JSON that might trip up our program that consumes JSON. And you can use this to generate many inputs at a time, just like that. And just to give you another example of how that can all work, I'm gonna just quickly go to the URL example. And so there you go. See, if you were building, for example, maybe you're a developer working on something like Firefox or Chrome, and you want to make sure that URL bar that you type URLs into doesn't sort of crash or produce weird results when it should actually consume a normal URL. So you can use something like this if you have an idea of the grammar of your language to more effectively fuzz it and make sure that you're actually building your program properly. And if you think back to our little fuzz.sh, because this is a command line utility, you can basically replace this Redanza utility here with Dharma and begin to fuzz your program using grammars. So finally, we're going to go to our third section for now, which is feedback fuzzing. And feedback fuzzing is where things start to get really interesting because it's where you start to see the power and sort of the intelligence of fuzzing tools. So we're gonna use a tool called GoFuzz, and GoFuzz is similar in theory to fuzz.sh in that it runs a program many times per second, generates inputs, and tries to find bugs. Where it's different is that if a single input that it tries covers new code than previous ones, it's saved for further mutation. So, for example, if we started with 4 seeds and then GoFuzz found a new input that covered new lines of code, it would save that as a 5th seed to have new things to generate inputs from. And that's sort of where the power of feedback fuzzing and genetic algorithms comes from. It's this idea of being able to use code coverage instrumentation to actually push the fuzzer further along. And so what we're going to do is we have another thing here it's in a package called fuzzme, but it's a method called broken method. And again, this broken method has a very small bug, but it's a very difficult bug to find because it only occurs in very specific cases. So what we're going to do first, I'm just going to leave that for now. We'll look more at what the bug is in a second. But first, I'm just going to try and fuzz this program with our little fuzz.sh program. So we've sort of wrapped it in the main.go here, so we can still read from the file and sort of treat it the same way as we did our other program before. So what I'm going to do is I'm just going to sort of access the fuzz.sh from our first section and run our broken program again with the seeds that we see here. And so I have some different seeds this time. I just have F, U, and Z. That's it, because it looks like this method sort of works with those characters a lot. So that's kind of a good place to let the fuzzer start. And so if I run this, what you'll see is that it'll generate a bunch of inputs. And I could let this run for a very long time. I let it run for, I think, 5 minutes at one point. But if you let this run for days, the likelihood is that it would never actually find the bug that we're trying to find. And that's because in some cases, the bugs are triggered by very specific inputs. As you can see here, if you've read the comment above, it'll try to read the 4th index of data, even when it only has a length of 3. So to trigger this bug, we need the exact string fuz inside data. No more, no less, no other characters on either side. And that's really difficult for this fuzzer to actually try and find because it doesn't have any idea of progress that it's already made. It starts from scratch every single time. So we're going to use a tool called GoFuzz to actually fuzz this properly. And so GoFuzz sort of manifests its interface in a very similar way to fuzz.sh, except instead of reading in from a file, it just reads in bytes directly from an array. So we're just gonna do exactly what we did in our file, take that data and turn it into a string and run our method with it. If you look at the README online, what you're going to see is that we're actually using GoFuzz build to build this program, not just to Go build itself. And that's because GoFuzz build does something really important. It instruments this code for coverage. And what that really means is that it sort of inserts extra detections into the code that allows GoFuzz to understand which lines of code have been covered and which ones haven't. And that's sort of where the power of this comes from. By instrumenting the code and adding those extra lines, GoFuzz is able to understand inputs on a deeper level by knowing which parts of the code they trigger and focus on parts of the code that they haven't triggered. So we're gonna run GoFuzz. If you run GoFuzz build, you'll see that it outputs a fuzz.zip, which is basically our binary. So we're gonna go ahead and just run GoFuzz with fuzz.zip. And work directory is seeds. That just says here are my initial inputs, same as before. And so what you'll see here is that very, very quickly we'll get a crash, actually immediately. GoFuzz is very effective. And this is, while it was a tough problem for fuzz.sh, it was a trivial problem for GoFuzz. You also see some interesting stats, like the fact that we were running 2,000 tests per second. So GoFuzz is, a little more fully featured, obviously, than our simple shell script. But let's actually take a look at the work directory and see what we were and see what happened. So the first thing you'll notice is that there are 3 folders here. Corpus and crashes are the important ones. Crashes obviously has our bug, and we'll take a look at that in a second. But first, we want to look at the corpus. And the corpus is sort of GoFuzz's existing list of seeds. So it'll take these existing seeds, the F, U, and Z, it'll bring those into the corpus, and it'll start playing with them and mutating them. And any seed that covers a new line of code, it'll add. So you can see that we gave it 3, but it's now settled at about 5. And so if we look through all of these results, we can see that this one probably didn't generate anything, but we can sort of go through and, oh dear, a lot of these files are actually have strange encoding. So let's take a look at them. Actually, we can open it anyway. How about that? There you go. Okay, we're just gonna. So sometimes you get this with fuzzers because by nature they, great at actually generating tests that are sort of difficult for files to read, and Visual Studio Code has decided that it didn't want to open some of those files because it saw characters it didn't understand, and that's that question mark right there. So let's put those next to our method and take a look at what they actually did. So, and we can and the nice thing about this corpus is that we can sort of track the progress of the fuzzer and see exactly what it did over time. So there you go. So it started off with F, and it decided to try and add a random character to it. And that obviously didn't do anything. But what GoFuzz did is said, oh, okay, well, we covered this line of code, and that was true. So we also tried to execute this, and that was false. So we stopped there. And so it saved that because it had never seen line 8 before. And so what we can do now is take a look at what happens next. And if we find the right file, that'll come in a second. There you go. So now we had FU. So what that means is that the fuzzer, ran through more, ran through F. That was true. It hit the fact that U is also part of the string in the right place. True. And it went to the next line, and that was false. And so it saved that as another input to possibly test, because it had covered a new line of code that we hadn't seen previously, line 9, and so on and so forth this way until we get to, I believe it was this one that actually produced FUZ. And FUZ basically meant that it had covered all of the lines of code, but it didn't produce the bug because we actually had a string of like 4, not 3. And if we go and look at the actual crasher, I think what we'll see is that it is just the string FUZ. And so the mutation that happened there was it ran input that generated some new code, and then it said, okay, to mutate this, we're going to remove that strange byte at the end of the string, which resulted in FUZ. And if we take a look at the output here, we're going to see that there was actually another index out of range panic. So that's sort of an example of how feedback-driven fuzzing can really, push your fuzzing campaign forward, where normal fuzzing, mutational or grammar-driven, without feedback, tends to fall down. So I'm going to switch back over just for a second to the slides to sort of come through and first I can take 1 or 2 questions now if they're pretty small. So I don't know if there's any in the chat that Andre haven't answered. He's doing a good job. But if there's any questions that people have quickly, you can ask them here. But I will ask again before the end. So don't feel any need to get your words in now. All right, sounds good. Okay, I'm gonna move on then, since it seems like Andre's keeping the chat down pretty well. So I'll push on. So now that you're familiar with some widely used fuzzing tools, I'm going to take you through a 4-step fuzzing workflow that you'll be able to take and apply to your own code. We'll use it to look at what we could have done to find Heartbleed back in 2014, and we'll also apply it to find a vulnerability in a web application, just like you could with your own software. So the first step to any successful fuzzing campaign is to know your attack surface. This is the area you're concerned about hackers attacking and is generally the first part of your code base that you should fuzz. A great place to start is with trust boundaries, which we can define as any place where untrusted data crosses a boundary into your application. For web apps, this could be something like a form input. In a REST API, this would be any routes that accept post, put, or patch, along with any headers and query parameters. Trust boundaries are such critical parts of a code base that fuzzing all trust boundaries of a code base is actually a critical step of Microsoft's Security Development Lifecycle, or SDLC. When you think of OpenSSL, the code that Heartbleed was found in, the one thing you always need to do with an SSL connection is make the initial SSL handshake. So for an OpenSSL fuzzer, that's probably a good place to start, just throwing some data into the handshake and seeing if that causes any bugs. So let's take that same thinking over to our REST API to see where the attack surface might be there. All right, so as I mentioned, the attack surface for Heartbleed, the interesting one there is that is the Heartbleed handshake. So we do have a handshake fuzzer, but I'm going to leave that for the next section because this one's purely about attack surface. So for attack surface, we have a small web application here. As you can see, it has one route, RLE, and it runs on port 1323. And if we look at handlers, we can take a look at the actual handler for RLE. And if we would read through this, what we'd get is that this is basically a small web service that that if you provided the payload, it'll run length encode that payload for you. And so I'm just going to run that through quickly to show you what that means. So if we just run the main, oh, my bad, need to be in the right place. If we run main.go, we're going to see that it starts up a little web server, and we're just going to send it a JSON payload. And so this JSON payload has the string to encode with letters ABC and then a whole bunch of Ds at the end. And if we make a request for that, we're going to see that we get a run length encoded payload back, which is, we get 1A, 1B, 1C, and 10 Ds, which seems about right. Everything seems good so far. You guys probably realize by now that there will be a bug in here somewhere, but for now, this is exactly what looks like exactly what it should be doing. So if we think about the attack surface of this, if we actually take a look at the handler, what we know, and I'm just going to go here to save us some time, what we know is that it basically looks at the JSON body of the post and puts it into this this request structure and then reads the string out of here. So in general, we probably want to fuzz the JSON body, and that could change depending on the web app that you're testing. You might want to fuzz, the authentication header, or potentially some query parameters. But we know that for this handler, the thing that we're actually reading is the encode request. So we're going to start off by fuzzing that. So what's the next step? After harnessing your code, after looking at your attack service, the important part is to harness your code. And in practice, harnessing your code is the art of connecting your input generator to your code in some way. So beforehand, the harness was just our simple fuzz.sh method. And harnessing in general is a huge topic and something that needs to be done with care, since a bad harness might not test the important parts of your code. Take a front-end application, for instance. If you write a harness that types data into form fields, but never exercises the page by clicking the buttons in a random order, then you're ignoring key parts of your application and you'll never find any bugs that have to do with button presses, only text inputs. In general, you want three things from a fuzz harness. You want it to be fast. If you're trying to run hundreds or thousands of tests per second, then by definition, you want your fuzzer to be able to run one test as fast as possible. A good harness is also robust. You only want it to report bugs when something truly unexpected happens in your code. And an example of this is if you're fuzzing a function and you expect it to throw a certain kind of exception. You should catch those in the harness since they're part of the expected behavior of the software. Then you can be certain that any exception raised while fuzzing is something that you didn't expect. Another example of this is HTTP error codes. An application returning a 400 in response to an invalid input is good, since it's telling the user that they made an error. A web application returning 500 is a true bug, since a 500 signals an unexpected internal server error and something that should be fixed. Finally, your harness should be well scoped. Scoping your fuzzer will allow it to run faster. So if you want to test a specific part of your application, break it out and target that section directly, rather than fuzzing your entire app just to test a small portion of it. Let's jump back to the demo quickly and take a look at writing a harness for OpenSSL and for our web application. So we're going to take a break from our REST API quickly and go and take a look at OpenSSL. So as we mentioned before, what we get here is what we're going to fuzz here is the handshake. So I'm not going to go through this entire file with you, but the gist of it is we're setting up a server that we can make the handshake with. We're taking an input, and I'll just back up quickly and talk about this. So OpenSSL is obviously written in C++, so we can't use GoFuzz for it. What we can use is libfuzzer. It's a fuzzer that's sort of part of the Clang toolchain, and it's very, very similar to GoFuzz in that it'll run a single method with an array of bytes many, many times and pass your code the data in that way. So we can use the same principle and set up a server ready to accept handshakes, write data to the server, and then actually do the OpenSSL handshake. And that should at least give us a starting point for our fuzzer. So coming back to the REST API and looking at it from the same place, the question is, what's the ideal place to harness here? We could hook up a fuzzer to a command line utility like curl and pipe something like Redanza intermutation. That would work. But we all know that the network is quite slow, and we wouldn't get very quick fuzzing. Nothing on the order of tens of thousands of tests per second. Also, the Go network code has actually been fuzzed quite extensively, so we'll really just be wasting CPU clock cycles since we're not actually adding anything by testing that code. We could just fuzz by putting code directly into the JSON payload too. But since JSON decoding code of Go is also very well tested, and that's what's happening here, we're just taking the JSON from the body and decoding it and putting it into the structure. So since that code is also very well tested, we'd actually be waiting a bunch of cycles here. What we really want to test is this handler that run length encodes the payload. So what we're going to do, and you can see this in our fuzzer right here, is again, like GoFuzz before, we're using GoFuzz again for this, so we consume a bunch of data. All of this code is essentially scaffolding that builds up a fake network request, so that our handler that we're fuzzing thinks that it's actually being hit via the network. And then the final step here is that we call our encode handler with the context that contains the data. And so you can see here we've actually just put the data from the fuzzer into the encode request structure, and then we're gonna send that over just like normal request, and we're gonna see if it can find any bugs in the code that way. So why don't we actually go ahead and run our fuzzers? So I have a separate tab here just because for OpenSSL it helps to run this in a Linux container. And if you go and take a look at the README in the repository, it gives you the instructions on how to set all of that. And so what we want to do here is basically we've compiled our handshake fuzzer down into a binary with libfuzzer that we're now going to run. And so we're running, and as you can see, we haven't caught a bug yet. And of course, with fuzzing, there's always the opportunity to find bugs much further down the road, and you should be fuzzing continuously. So that's not really an issue, but I'm looking for a quick bug here, and I haven't found anything. It's a little strange, but we'll get to that. Just sort of let that sit for a second. We're going to go back over to our web application, and again, I've compiled that down with GoFuzz to a binary, which is sitting right here. So we're gonna try to actually execute and fuzz that too. So if I just run GoFuzz with fuzz1.zip, sorry, gotta make sure that I'm in the right place. There we go. So we're going to start GoFuzz. And interestingly, again, we're actually going to see that we're not getting any bugs. And now, as I've already said before, fuzzing is a long learning process, and we might find them later. But I want to find bugs now, and I'm not. So let's talk about why. So it turns out that, of course, the fuzzing and choosing the right fuzzing tool, the right data generator, is only half the battle. We've already talked about choosing the right fuzzer. So we have fuzz.sh. For Go, we're using GoFuzz. For Heartbleed, we're using libfuzzer. But instrumentation is really important, and that's kind of a new concept here. Essentially, it means adding extra detectors to your code that can make fuzzing more effective, whether that's code coverage feedback or libraries that cause your code to error out when certain conditions are met. So let's sort of go back to our fuzzers and take a look at what kind of instrumentation we can use to make them a little more effective. So going to the Heartbleed OpenSSL fuzzer one more time, I'm going to introduce a new tool, and this new tool is something called Address Sanitizer, or ASAN. And so if you go and look at the README for the Heartbleed bug, you'll see that right at the bottom there, what we actually do is we recompile our fuzzer with Address Sanitizer, and that's a tool that's part of Clang and the whole tool chain that it gives you. And essentially, what it does is it adds detections throughout your code that essentially map out the entire memory space of your code. So we know that Heartbleed was a memory corruption bug. So if we wanted to fuzz OpenSSL for memory corruption bugs, we need to actually, connect it to a detector that can look for memory corruption bugs and actually crash it when that happens, because memory corruption doesn't always result in just a straight up crash. So if we recompile the exact same fuzzer, no difference, but with Address Sanitizer, and we execute that, we'll actually see that we'll find a bug quite quickly. And this might take a few seconds, but we're going to see that very, very soon it actually detects a bug. And there you go. So what we just did there, exact same fuzzer, no difference in terms of the code that we wrote. We just added a special little detector called Address Sanitizer. And if we scroll up to the summary, we can see that Address Sanitizer says we found a heap buffer overflow on a certain address with a read of size 63,000. And that's our bug. That's Heartbleed, because we know it was a memory leak, right? So that's generally an unbounded read or a read out of bounds. So there you go. We wrote a fuzzer, very simple. It just sends some data to a server and makes a handshake. But the tools that we used to instrument a fuzzer were the important part that actually caused the crash. So let's sort of go back to our Go web application and see what we can do there. So if you think about this from the perspective of invariants, it's kind of an interesting way to do that. So an invariant is something that you always want to be true. And in unit tests, in general, you can make that invariant very specific. You can say, I want to put this value in, and I know this value should come out. When it comes to fuzzing, you're running many, many values per second, so you're not always entirely sure what value you need to, what your invariant should be. Because right now, all our invariant is this program doesn't crash. And many programs don't straight up crash. So we need to try a little harder to actually try and find a bug. What we do know, however, is that this program run length encodes a value. So if we're run length encoding properly, then of course we should be able to decode the thing that we encode and get the exact same value back. And that can be an invariant that is true for everything, right? Because no matter what we do, we should get the exact same value back out. So we can actually add some code in here that does that. And so I just added in this little snippet here, and all this does is just get the response back from the handler that we ran, and said, okay, so if we decode the thing that we just got back, and we compare it to the original test before we ever sent it over to the server, do we get the same thing? And if not, then we're going to panic, saying, hey, we actually found a bug because the web server works and doesn't crash, but semantically it does the wrong thing. And we're going to try and run that now with the second fuzzer, which has this sort of extra detection in there. And if we execute that, you'll see that very, very quickly, we're actually going to get a crash. In fact, right away. And if we go look at that crash, it'll show us that we got panic with decoded not equal to encoded. And so it turns out that we actually made an error while writing this code. And so you look at the one unit test that this developer wrote, they unfortunately chose the one test that will actually cause this code to pass. Because if we go and take a look at our implementation, we actually forgot to reset a counter. So what that means is that because we're only run length encoding one thing that happens more than once, this test actually works. And you can see that it'll just run it and it'll come back and say, yeah, that's all fine, test passed. But if I were to put, something else for it to run length encode, this test would fail immediately. So again, this is another example of how developers not thinking of every possible scenario can cause problems in testing. So, and if we went and fixed this bug and saved that and went back and ran this test again, we'd see that it passed. So again, fuzzing helped us find a bug that a developer missed, and we just had to add a little bit of extra detection to make sure that we could find that bug properly. Okay, and so the fourth step in any fuzzing campaign has to be to continuously fuzz your code. Because of the nature of software, there's no guarantee that your code is ever completely bug-free. And there's a famous quote from Dijkstra that actually says as much. Testing can show the presence but not the absence of bugs. And in that vein, if you run 1,000,000 tests on your code, you don't have a guarantee that the 1,000,001th test you run won't exercise a new edge case and catch a bug. The only way to be sure that you're exhaustively testing your code is through continuous fuzzing. This should be hooked into your continuous integration tooling too. As developers update code, the fuzzer should automatically pick up and begin testing the latest changes. That way you can ensure you're catching bugs before they ever reach production. We've seen this in practice many times. In 2019, about half of all the exploitable bugs found in Google Chrome were in code less than a year old. New code always has bugs, so we should never stop testing it. Luckily, there are some tools out there to help you, so you don't need to automate and manage all this by yourself. So the first example of this was actually a very tiny release. Microsoft recently released OneFuzz at CPPCon, which is a tool that lets you orchestrate and scale libfuzzer and AFL targets. If you're very experienced with the ins and outs of fuzzing and you're okay with setting up and managing a service yourself, this might be worth looking into. It might not be as useful if you're new to fuzzing or need help with the basics. Google has a similar service that you can run yourself called Clusterfuzz, and it's actually the same infrastructure used internally by the Google Chrome fuzzing team. It's similar to OneFuzz in that it's libfuzzer and AFL focused, and you need to set it up and manage it yourself, but it goes a little further by providing a UI to view bugs and statistics in as well. And of course, there are also platforms like Fuzzbuzz. Fuzzbuzz is a little different in that it offers a fully managed solution and tries to make fuzzing as accessible as possible for developers to get started with and helps them fit it into their continuous integration pipeline by hooking into source control tools like GitHub and productivity tools like Slack. What I'm really saying here is that there's a tool out there for you. Whether you're a seasoned professional or brand new to fuzzing, there's really no excuse to not have it tightly integrated into your software development workflow. Heartbleed took everybody by surprise, and it cost the world huge amounts of time and money. It goes without saying that we'd all prefer to not be surprised again. So if you take just one thing away from this talk, make it this. Stopping the next $1 million bug will be a joint effort between developers and security teams. And the first step to stopping it is to changing our mindsets. Start approaching testing from the perspective of assuming your code has bugs, and then asking yourself how to find them. Next, make fuzzing just as important as unit or integration testing at your project or company, and try to ingrain it into your development culture as much as possible. And finally, continuously fuzz your code, because modern code bases are always changing, and engineers need all the help they can get. With that, I'd like to open up for some questions now. If I don't get to you, or if you'd like to talk to me some more afterwards, you can shoot me an email or find me on Twitter. And if you want to look at what I talked about today, everything here is going to be available on my GitHub. So I'm gonna stick around now, and I'll see if I can turn my video back on and hopefully not have everything crash. And I'll take any questions if anybody has them. So it looks like there's no questions right away. So what I'm going to do is I'm going to stick around for a little bit. If you have any in the chat, just let me know. And if there's anything else that you want to message me about later, ping me on here and we can talk. Or shoot me an email, talk to me on Twitter. Always happy to talk about fuzzing. Thanks for coming.